Okay, class. It's been good to hear from each and every one of you. I know this has been a very rough transition. Um, the onset of the COVID-19 virus has forced us to shut the school down and go to a fully online scenario. It's been quite an adjustment for us. I know that that doesn't even begin to capture um, what each and every one of us is going through. Um, yeah, it's been rough for us. I know it's been rough for you. Um, I want to thank everyone who showed up this past Friday. That was the day when they were giving out the laptops at all of the Broward County schools. If you were watching the news, over 64,000 laptops were provided to students, and that was both high school and post-secondary students. By far and away, most of the students in the Broward County Public School District are high school, but we do have our three technical colleges, Atlantic, Sheridan, and of course, McFadder Technical College. So for our class, we'll be presenting this fully online. Going to be a little bit different scenario, a little bit different situation, but we're going to get through this. So I'm going to be recording lectures for each one of our lessons, and then I'll also be recording the accompanying video for our lab. Let's get started. Lesson 1, implementing IPv4 and IPv6 addressing. Our overview, our objectives: understand how to configure IPv4 addresses and options. Determine and configure appropriate IPv6 addresses. Configuring subnetting, stateless addressing, interoperability between IPv and IPv6 using ISA-TAP 6-4 and Teredo. Okay, so first off, we're taking a trip in the Wayback Machine. We're going back to your Network Plus class. So some of this is going to be easy, some of this might be new. We may have done book reading. Some of this you may not have done before. Hopefully you did. If you did your previous labs, this is going to be a walk in the park. So we'll be using IPv4, IPv6 to make our connectivity, designing names, resolution strategies. Understand that when our computers are accessed, we typically communicate using their host names. Every device that connects on your network and the internet must have an IP address. We need a way to associate those names with their IP addresses. If you'll remember from our Network Plus, the IP Internet Protocol, it's responsible for the addressing information, adding the addressing information to the packets. The TCP/IP, Transmission Control Protocol, Internet Protocol, is a set. It's a set of protocols that allows computers to exchange that data. Why IPv6? We've talked about this numerous times. There is a limit on the number of addresses available for IPv4. Basically, they've all been consumed. If we tried to provide a public IPv4 address to each and every device, we would not have been able to do that years ago. It would have stopped. Plus, you've got the entire security issue of having an internal device being given a public address. We have the ability to set private IP addressing using our various types of NAT, using routing. We can use IPv6, and if you'll remember from Network Plus, your device can have up to 3 IPv6 addresses. In working with IPv4, remember that that translates to a 32-bit address, 4 8-bit octets. The portion of that that indicates which network you're on is called the network ID. The remaining bits, and remember the network ID is to the left, the host portion is to the right, those remaining bits are the total up to be the total number of hosts that can be on the network. It also is the host ID. That's when we're dealing with subnetting. If we take a look back, we have our Class A, Class B, and Class C. Understand that for the most part, we're not going to deal with Class D and Class E. Class A IP addresses in that first octet will range from 1 to 127. If your network ID falls into the first and second octets, it has a range of 128 to 191, and that is a Class B address. If your network ID encompasses either the first, second, and third octets and has a range of 192 to 223, that is a Class C address. Note the examples. In a Class A, there are 126 networks. Each one of those networks can have 16,777,214 hosts. Not very efficient. If you're in a Class B space, you can have 16,384 networks. Each one of those networks can have 65,534 hosts. Well, if you've got 16,000 really large companies, maybe that works for you. And not really. Class C is where we see most of our ranges, and you'll recognize that 192 number for the range is almost every one of our homes. The Class C space can have 2,097,152 unique networks, each hosting 254 hosts. When we convert that to binary, when we look at this, what does this represent? This is our subnet mask. This is a classful subnet mask. Class A, the first 8 bits are turned on. Class B, the first 16 bits are turned on. And in Class C, the first 24 bits are turned on. Subnetting is how we break those larger networks into smaller networks. You've seen this before. You'll be learning this all over again. So if we want to subnet, we want to break a larger network into a smaller network. For example, this Class B range. Class B range, as we saw in our prior slide, can have many hosts. But you don't need that many. Using the 255.192 subnet mask, you can chunk that into smaller networks. So you can see your network ID of each one of the networks. In other words, what's that beginning address? Because remember, you can't use the first address, you can't use the last. The network address starts at 0, actually ends at 63. Usable is 1 to 62. Remember, 0 is a number. How many IPs are actually in this network? 64. 0 to 63. That's what that 192. If you see a subnet mask that ends with 192, you should immediately know that the network size is 64 IPs minus 2, which is for the first and last, so you have how many? 62 usable IPs. The next network range starts at 64, ends at 127. Usable 65 to 126, and then so on. This is classless interdomain routing, using more efficient what do we use NAT for? We use NAT to allow many private IP addresses to represent themselves and be able to get to the internet behind a single IP address. So if you've got a network with 200 computers, do you buy 200 public IP addresses? No, you have one public facing IP address. You use network address translation to allow those 200 to be able to hide behind and gain access to the internet. Note the last bullet point. In other words, it allows multiple computers on a network to connect to the internet through a single IP address. And I know that I'm stumbling through a couple of these words. Just like you, this is our first time doing fully online. Bear with me. It'll get better. So we move into, and we're looking here, IPv6. IPv6 gives us quite a number of benefits. First off, it's a 128-bit address instead of a 32-bit address. If you'll remember, every time you add an additional bit, you're doubling the size. If you have a single bit, it has two values, 0 or 1. If you add a second bit, it also has two values, but now you can be 00, 01, 10, 11, 4 values. If you add a third bit of a 0 and a 1, you double it again, you now have 8, then 16, 32, 64, and so on. Imagine how many more IP addresses are available when you go from 32-bit space to 128-bit space. Double, 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 double. Using IPv6 for all effective purposes, we won't run out of IP addresses, at least not for a long time. It's much more efficient for routing. It supports automatic configuration. Whereas in IPv4, if we see our system get an APIPA address, it's more or less a stopgap because something went wrong. We expect that something's not connected. We ran out of DHCP addresses that can be handed out. There's a problem with connectivity. With IPv6, we utilize that to provide connectivity on our local network. And it's much more secure. There's 3 different types of addresses. Unicast, which is 1-to-1, multicast, which is 1-to-many, and anycast provides 1-to-one of many transmission to groups of interfaces. We can have 3 different types of addresses. Unicast addressing is divided into global unicast, which is our public IP address. The local link address, which is a private, non-routable address confined to a single subnet. Sound familiar? Or unique local address. This is also meant for private addressing with the addition of being unique so that joining 2 subnets does not cause address collision. So a unique local address can work across subnets. We can have stateless auto configuration, stateful auto configuration, and both. Remember what our default gateway? Also called a router. It allows our local network to connect to other networks or the internet. If we have dissimilar subnets, we have to have a way to be able to enable them to communicate with each other. That's our router. How do we resolve the names to IP addresses? We use DNS, Domain Name System. We can integrate that with our Active Directory, which is we saw when we created our domain with Active Directory, DNS, and DHCP. DNS uses what we call an FQDN, fully qualified domain name. For example, in our lab environment, we're using the datum.com domain environment. Our domain controller we've named LON-DC1. Its fully qualified domain name is lon-dc1.adatum.com. lon-dc1.adatum.com. We can configure our IP addresses either manually or automatically. And as before, we've got step-by-steps on how to define static IP addresses. We'll be looking at this in our lab. So I'm going to scroll through these step-by-steps. No point in me reading all this to you when we're going to do it all again in the lab. And now we can do this in both a command prompt and PowerShell to view our information. So at a command prompt, we can type ipconfig and press enter, and we'll see a brief description. Remember, you can also use ipconfig /all to get the information for all your IPs that are IP adapters that are configured, and get detailed information on each one. If we do PowerShell, we can use PowerShell to resolve DNS. Just the same way as on command we could use NSLOOKUP, we can use the resolve-DNS name and the website address to resolve a website. We'll be looking at implementing stateless IPv6 addressing. Here again, step by step. So you can do this through PowerShell. Here again, we're going to do this in our lab, so I'm not going to read you each and every one of these steps. It's kind of redundant and it's a waste of your time. And I know you want to get into the learning, you want to do your reading, you want to get the actual skills necessary to do this. That's called competency based. That's why we do this. There are ways to transition from IPv4 to IPv6. So what if you don't fully support it? You can use these transition technologies to help bridge that gap. 6 to 4 allows IPv6 packets to be transmitted over an IPv4 network. So you haven't fully implemented IPv6. Well, that doesn't stop you. Here again, step by steps. We'll be covering this more in our lab. How to add a computer to the domain. What is ISATAP? It's an automatic tunneling protocol. So it allows you to emulate an IPv6 link using your IPv4 network. A lot of slides, right? Like I've told you in our classroom, same thing here. I am not going to give you death by PowerPoint. What is Torado? It is an IPv4 network address translation traversal, NAT-T for IPv6. What does that mean? That one of the advantages of Torado is that it will function even when IPv6, IPv4 hosts are located behind IPv4 NAT. Okay, so real briefly, in this lesson we kept it to 20 minutes. I don't want to see many of these lessons go over 20 minutes. When you're accessing computers from a network, you typically communicate by using their host names. If you're accessing a website, you use a friendly name. Well, we can't remember IPv4 or let alone IPv6 addresses. We use that friendly name Microsoft.com to get to the website. Your computer needs a way to translate that. How does that name translate into an IPv6 or an IPv4 address to its destination on the internet? We use subnetting to break a large network into smaller, more usable, more efficient segments. So while a Class B address has more than 65,000 host addresses available for it, we can chunk that into smaller, more usable networks. Why are we using IPv6? Because IPv4 addresses, well, here it says running low, they're used up. IPv6 takes care of that problem for us. Even though IPv6 has been around for a number of years now, for the most part, we're still using IPv4. There are methods that are in place that allow for that transition. 6 to 4, Torado, the ISA-TAP, and that's Intra-Site Automatic Tunneling Addressing Protocol. These are all to smooth the transition from IPv4 to IPv6. I hope you've enjoyed this lesson. We'll be following this up with your lab.